Hello dear students, welcome to physics classes. In previous video we discussed about one derivation, that is nothing but a lens maker's formula. From that derivation we got one expression. That expression is nothing but 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. This is the expression in which we derived in the previous class, and that formula is called as a lens maker's formula. And this lens maker's formula is applicable while designing the lenses, right? These all things we are discussed in the previous classes. Now in today's class we are going to discuss about image formation in the case of thin lenses. Image formation in the case of thin lenses. We already discussed about the lenses, right? Now here we are discussing about the how image formation takes place in the case of lenses. But here we used one term, that is nothing but thin lenses. Then what do you mean by thin lenses? Before discussing about the image formation, we will discuss the meaning of thin lenses. So thin lens is nothing but thin lens is one whose thickness is negligible compared to the radius of curvature of its surfaces. Then it is called as thin lenses. Thin lens is one whose thickness is negligible compared to the radius of curvature of its surfaces. Now let us understand what you mean by thin lens briefly. See here, I am going to take one convex lens. This is one convex lens. And again I am going to take another convex lens. Both are the convex lenses. But if you observe the first convex lens, the thickness of the first convex lens is more compared to the thickness of the second convex lens. That means this lens is thin, right? So the second lens is thin compared to the first convex lens. See here, thin lens means the distance between the two surfaces of the lens. That means we know that lens has mainly two surfaces, right? And the distance between these two surfaces are too small in the cases of thin lenses. Okay, so such lenses are called as thin lenses. See here, the thickness of the first lens is more. That means the distance between the two surfaces is more, right? In the second case, the distance between the two surfaces is too small compared to the first lens, and that thickness is very small. That means it is negligible compared to the radius of curvature. If you compare that thickness with the radius of curvature, we know that radius of curvature is nothing but it is the distance from an optic center to the, suppose that if I take this is an optic center, it is the distance from optic center to the any point on the surface, right? That is called as a radius of a curvature. If you compare that thickness with the radius of curvature of the lens, then the thickness is negligible compared to that of a radius of a curvature, right? Then it is called as thin lenses. Suppose that if you take a concave lens also, if you take concave lens, the thickness, that means the distance between the two surfaces is too small, then such lenses are called as thin lens. Now let us see image of an object formed by the thin lenses. Now let's see the first case, case 1. Case 1. In case 1, I am going to take an convex lens. This is a thin convex lens I am considering here. Okay, and we know that exactly the center of this lens is called as optical center, that is C, and the line which is passing through this optical center, that line is called as principal axis. Okay, to get an image, we know that to get an image we should take one object, right? So here I am going to take one object AB. This is an object which is perpendicular to the principal axis. Okay, now see here, the lens has two surfaces, right? This is one surface and this is another surface. For both the surfaces, if I consider an focus, we will get there are two focus in this case, because for first surface I should take one focus, for second surface also I should take one principal focus. Now for first surface I am taking here the first principal focus, that one is F1. For second surface I am taking another principal focus, that is F2. This is the second principal focus for second surface, and these both the principal focus are equidistant from the optical center. This one you should remember. This principal focus, that means F1 and F2 are equidistant from the optical center. That means the distance from optical center to the first principal focus and the distance from the optical center to the second principal focus are same. Okay, and here now I am going to incident a ray of light from any point on this object. Here AB is nothing but an object. I am going to incident a ray of light or originating a ray of light any point from this object. Okay, any point on this object, coming from any point on this object. Here I am taking this point here, this point, and incidenting a ray of light which is parallel to the principal axis. This ray of light originating from the object, and that ray of light is exactly parallel to the principal axis. When the incident ray of light is parallel to the principal axis, then after refraction, we know that when the ray of light passes through the lens, it will undergo the refraction, right? When it undergoes the refraction, then after refraction, that ray of light will pass through the second principal focus. That one you should remember. Okay, when the ray of light incident parallel, when the ray of light incident parallel to the principal axis, of the lens, then after refraction, light ray will pass through the second principal focus, in the case of a convex lens. This is in the case of a convex lens, thin convex lens. Now let us see in the case of a concave lens. Suppose that if I incident a ray of light parallel to the principal axis in the concave lens, okay, then what will be the result? That one we will see. See here, in the case of a concave lens, I am going to take here concave lens. This is the thin concave lens. Here also I am taking one lens, that is a concave lens, and exactly the center of that concave lens is called as a optic center. This is the optic center, and the line which is passing through this center is called as a principal axis. Okay. Now here also I am going to take one object. That object is AB. And here also there are two surfaces. So that I should take, there are two principal focus. And here this one is the first principal focus and this one is the second principal focus. And another thing you should remember that the first principal focus always on the object side. Okay, you should take the first principal focus always on the object side. Understood? Now here also I am going to incident a ray of light parallel to the principal axis. See this ray of light which is parallel to the principal axis. Then we know that in the case of a concave lens, it diverges the incident ray of light after refraction. Right? After refraction, this incident light ray will diverge. It will diverge like this. But this diverged ray of light appear to diverge from first principal focus. Okay? This will appear to diverge from first principal focus. This is possible only when you incident a ray of light parallel to that of a principal axis. So that when you incident a ray of light parallel to the principal axis in the case of concave lens, then after refraction this light ray appear to emerge from first principal focus. Okay, that is the first case in the case of convex lens and concave lens. How the refraction takes place if you incident a ray of light parallel to the principal axis. Now let us see the second case, case 2. Case 2. In case 2, I am going to incident a ray of light through the optical center. When a ray of light passes through a optical center. See here, now I am going to incident a ray of light through a optical center of both the convex and concave lens. Then what will be the result? That one we will see. Now in the first, I am considering first convex lens, thin convex lens. This is an thin convex lens. Okay. And here I am again taking a principal axis. This is the first principal focus F1. This is the second principal focus F2. And this is an object AB. This is the optic center. Now I am going to incident ray of light, and that ray of light which is passing through this optical center. Suppose that if I incident ray of light like this, that ray of light which is passing through the optical center, and we will see there is no any deviation after refraction. Okay, that is very important. When a ray of light passes through a optical center, then there is no any deviation after the refraction. Okay, that is in the case of a convex lens and also in the case of a concave lens. In the concave lens also you will not observe any deviation of the ray of light after refraction. See here this is the optic center. This is the first principal focus. This is the second principal focus. This is an object AB. Here also I am going to incident a ray of light which is passing through the optical center, and here also there is no any deviation you will observe after the refraction of light. So this is the second case when you incident a ray of light through the optical center. Now let us see the third case. Case 3. In case 3, I am going to incident a ray of light, and that ray of light which is passing through the first principal focus in the case of a convex lens. See, in the case of convex lens, now you see in the case of a thin convex lens, here I am going to consider a thin convex lens, and this is the principal axis, this is the optic center, first principal focus, this is second principal focus, and here I am taking an object A, B. Okay. Now I am going to incident a ray of light, and that ray of light which is passing through the first principal focus like this. And after refraction, when it undergo the refraction, that light ray, emerged light ray, will be parallel to the principal axis. Okay. So when you incident a ray of light, and that ray of light which is passes through the first principal focus of the convex lens, after refraction, that emerged ray exactly parallel to the principal axis. That is the another case. That is in the case of a thin convex lens. Now we will see in the case of a concave lens, thin concave lens. Thin concave lens. See here, I am taking one thin concave lens. This is the principal axis, optic center, first principal focus, second principal focus, f2. And here I am taking one object AB. This is an object AB. Okay. See here, I am going to incident a ray of light here, not through the principal focus. Okay. Here I am going to incident a ray of light like this, and this ray of light which is appearing to meet the second principal focus. Here I am not going to incident ray of light through the first principal focus. Here incident a ray of light, and that ray of light appearing to meet at the second principal focus. That means if I extend this line or this ray of light, it will meet at a second principal focus, but because of this lens it will undergo the refraction, but actually after refraction this incident ray of light will not meet the second principal focus, but after refraction it will emerges like this, and that emerged ray of light exactly parallel to the principal axis. Okay, so we can tell that in the case of a thin concave lens, suppose that the incident ray of light appearing to meet at a second principal focus, after refraction the light ray, emerged light ray, will be parallel to the principal axis. That is in the case of a concave lens. But in the convex lens, when you pass through, when you incident a ray of light, and that ray of light pass through a first principal focus, after refraction the emerged ray of light will be parallel to the principal axis. Okay, these are the main three image formation in the case of thin lenses. Now let us see how convex lens producing a real image for different object distances. See here, the first case, when object distance is more than the focal length. See here, I took one thin convex lens, and let f1 be the principal focus, first, that is first principal focus, let f2 be the second principal focus. and I placed one object, that is AB, which is perpendicular to the principal axis. And here the object distance is more than the focal length. We know that the focal length is nothing but it is the distance from optic center to the principal focus of the lens. Then it is called as a focal length of the lens. The distance from optical center to the principal focus, that is the focal length of the lens. Okay. Here I kept the object behind the first principal focus. That means here the object distance is more than that of the focal length. And here there are two light rays originating from this object. The first light ray, which is parallel to the principal axis, and that light ray after refraction will pass through the second principal focus, and the another light ray which is passing through the optical center, and after refraction we will not see any deviation in this light ray, and both the light rays after refraction they will meet at some point, and in that point we will get the image of this object. Okay, when the object distance is more than the focal length, then we will get the real and inverted image. See here, both the light rays are after refraction really meets, so that it is called as a real image. And if you observe the image is inverted. Okay, you will get the inverted image of this object, so that the image is real and inverted. When you place an object behind the first principal focus, or the object distance is more than that of the focal length. That is the first case. And in second case, see here, when the object distance between F1 and 2F1. Here I placed an object AB between F1 and 2F1. F1 is the first principal focus, 2F1 is the twice the first principal focus. Okay. In between, if I place the object in between F1 and 2F1, I am getting the image here, A dash B dash. This is the image of this object. After refraction we will get. Okay. And the image is real, inverted. See here, image is real and also it is inverted as we observed here. And the image size is large, so that enlarged. I mentioned here enlarged. When you place object between F1 and 2F1, you will get the enlarged image, and also the image is real and inverted. So that is the second case. In third case, when the object distance is more than 2F1. Okay, if the object distance is more than 2F1, that means I placed here object behind the 2F1. Then you will get the image here. After refraction of this light rays, you will get the image here, and you will get the real, inverted and diminished image of this object. Okay, here also the image is real and also it is inverted, and the size of the image is very small. Okay, size of the image is very small in the case. In this case, when you place the object behind the 2F1, that means when the object distance is more than 2F1. See here, the object distance is more than 2F1. That is the third case. See here, fourth case, when the image is at 2F1. Suppose that if you place an object exactly at 2F1, then what type of image you are getting here? See here, you are getting image here, A dash B dash. It is also a real image, inverted image, but the image is the same size of that of the object. The image size and object size is same. When you place an object at when the object is at 2F1. Okay, when the object is at 2F1, then the size of the image is the same as that of the object. That is the fourth case. And in fifth case, when object at infinity. Suppose that if you place object at infinite distance, okay, after refraction you will get the image here, okay, but you will get the image exactly at second principal focus, and the image is real and inverted also. But when you place an object at infinite distance, then you are getting image exactly at second principal focus. So that is about the how convex lens producing an real image for different object distances. We already discussed how convex lens produces an real image. Now we will discuss how convex lens producing an virtual image. See here, I took one thin convex lens, and you know that let f1 be the first principal focus and f2 be the second principal focus. See here, I placed an object AB between optical center and first principal focus. We know that the distance from optical center to the first principal focus is called as a focal length. See here, the object distance, that means object distance means it is the distance from optic center to the object. If you observe here, the object distance is less than that of the focal length. Suppose that object distance is less than that of the focal length, which type of image we are getting here? That one we will see. See here also I am taking, there are two rays of light. There are two rays of light which is originating from this object. The first ray of light which is parallel to the principal axis, after refraction they will pass through the second principal focus. And another ray of light which is passed through the optical center, and that ray of light will pass through the optical center without any deviation after refraction. But after refraction, both the rays of light will not meet at any point, right? So that here we are not getting a real image. But if you extend this refracted ray of light to the back, okay, both the rays of light refracted rays of light I am going to extend here, then we will get one point in which both the extended ray of light will meet, and there we will get the image of this object AB. That image I am taking as A dash and B dash. But here see, we are getting the image is on same side of that of a object, okay, and here image side is same that of the object side. But which type of image we are getting here? See here image is virtual. Why it is virtual? Because the rays of light after refraction they will not actually meet, so that it is not a real image. Because of extending the refracted rays of light we are getting the image, so that this image is called as a virtual image, and it is erect. See here, we are getting the erect image. Erect image means it is a straight image, and here no any inverted image we are getting, only the erect image getting, and the size of the image is large, enlarged. The size of the image is large compared to the object. Okay, so that we can tell that suppose that if the object distance is less than that of the focal length, we will get the virtual, erect and enlarged image. So this is the convex lens. This is how convex lens producing a virtual image. Now let us see how concave lens producing a virtual image. Okay, see here I took one concave lens. And here also there is a two principal focus. Let f1 be the first principal focus, f2 be the second principal focus. And you should remember that in this case, at all position of the object, you will get the image formed will be virtual, erect and diminished. That is very important. In the case of a concave lens, if you place this object in any position, okay, if you place this object in any position, you will get the image as a virtual, erect and diminished. See here, I have placed one object AB here. Okay, this object AB, which is behind the first principal focus. See here, there are two light rays which is originating from this object AB. The first light ray which is parallel to the principal axis, and after refraction, it will emerges like this, the first incident ray of light and the second incident ray of light which is passes through the optical center. But we know that in the case of a concave lens, the lens will diverges the incident ray of light. Right, we know that concave lens which diverges the incident ray of light. But if you extend this diverged ray of light, this ray of light will meet at the principal focus. That is only when you incident a ray of light parallel to the principal axis. And the second ray of light which is passing through the optic center, they are pass without any deviation after refraction. And these both the light rays will meet some point here. Right, and I will get the image here. I will get the image here. That image is A dash B dash. Here also the image is a virtual image. Why it is virtual image? Actually, after refraction, these two rays will not meet. Because of extending this ray of light, we will get the image here. So that it is a virtual image and it is erect. It is also straight image. Right, A dash B dash. It is not a inverted image. It is also a straight image, so that it is called as an erect image. And also it is a diminished. Diminished means if you observe, the size of the image is small compared to the size of the object, so that it is a diminished image. And in the case of concave lens, if you place the object in any position, then you will get the same type of image. Same type means virtual, erect and diminished. Okay, that is about the image formation in the case of thin lenses.